We've been looking in section 3.4. Your homework isn't due in this section for quite a while yet, but maybe you have other homework questions. Does anybody have homework questions?
When do we have to have the shapes later?
That's a good question. I'm thinking around October 20th. I sent an email out saying a date I suspected. In this class, I have a tentative syllabus because it depends how much we discuss some topic. So sometimes we take longer than I think, and sometimes we're faster than I think. But so you have like a couple weeks probably. Any other questions?
And will we like turn in the actual shape, or will we turn in a photo of the shape?
You'll submit a photo of the shape and bring the shapes to class. The platonic solids we'll look at together in class. Study group meets tonight. The Monday night study group is canceled because people haven't been going. If you like going to study group, make sure you keep going so that this one doesn't get canceled too. If Monday night was your preferred night, don't forget you can still meet one-on-one with tutors by going to the website and emailing the tutors. Online students can do that through Skype. Anybody have any questions? We're still looking at different sizes of infinity. Today we'll answer the question, is there an infinity between the cardinality of the natural numbers and the cardinality of the real numbers? So you can put down your suspected answer to that, if there's a cardinality between the cardinality of the natural numbers and the cardinality of the real numbers. If you remember what we had looked at for the sizes of infinity, we had the natural numbers cardinality was smaller than the real numbers cardinality, and we had proved that with Cantor's diagonalization proof. We did not look at the proof that shows that the power set of the natural numbers is equivalent in cardinality to the cardinality of the real numbers, but that is in fact the case. And then we found a set that was larger than the real numbers. So the cardinality of the power set of the real numbers. All the subsets, the collection of all the subsets of the real numbers. And then we could just keep going, because since the power set of the real numbers was in fact a set, and since we have Cantor's power set theorem that says for any set S, finite or infinite, the cardinality of the power set of S is strictly greater than the cardinality of S, we could find a larger set yet by taking the power set of the real numbers. In fact, we could just keep going forever, taking power sets of power sets of power sets, and so on. But we had not proved this Cantor's power set theorem. To prove Cantor's power set theorem, we have a proof very similar to the proof that the real numbers are a larger set than the natural numbers. So I'm going to remind you of how we did that proof by finding the missing number . So we found the missing number. If there was a way to put the natural numbers in a one-to-one correspondence with the real numbers, then there'd be a way to list the real numbers. And we found that if there was such a list, we could find a number that was not on the list. We focused on the particular decimal place. So we just had to be different in one decimal place. So for the real number that went with the first number, we made sure the first decimal place was different. And then for the real number that went with the second real number, we made sure the second decimal place was different. for the real number that went with the third natural number, we made sure the third decimal place was different. And we had a pattern established that created a number that was not on the real number list at all anywhere. It always differed by at least one decimal place. We're going to take that same approach, the Cantor diagonalization proof, to create a proof demonstrating that the power set of a set is always larger than the set itself. This should be in your notes from last time, and now we're going to prove Cantor's power set theorem. Well, we'll look at the proof. We won't prove it explicitly, but we will look at what the proof looks like. So we're going to find the missing set. We're going to find a missing set from any proposed one-to-one pairing of S with the power set of S. So let's go ahead and write down a set and a one-to-one pairing with the set that's proposed, and find a missing set to show that there is no one-to-one pairing. So let's just go ahead and write down elements of S and elements of the power set of S, which would be subsets of S. Because remember, the power set of S is all the collections of subsets that you can make of S. So first I'll list out S, and we'll make it alphabet letters. So this doesn't just stop at 26 letters though. Our alphabet, we're going to start with subscripts once it gets past Z. So we'll have A sub 1, B sub 1, C sub 1, and then we'll go on. When we run out of those 26 letters, then we'll have A sub 2, B sub 2, C sub 2, and so on. So we'll have an infinite set S. So here's a proposed pairing. We have A go with the subset of S, that's letters E and F. We'll have B paired with the subset of S, that's A, B, D, G, F. We'll have C paired with the subset of S, that's A, G, R, S, T, U. We'll have D go with the empty set. Remember when we were making power sets, the empty set was always a subset, so the empty set was always in there. We'll have E go with this whole set S, because remember one of our elements in our power sets was the whole set itself. And we'll go dot, 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 and then another set here. I'll just say Q, R, V, dot, dot, dot. Okay, so we have this infinite set. The way I described S, it's actually of infinity the size of the natural numbers because we're able to list it. And we have the power set of S. So it's a proposed listing of all the subsets of S. And we're going to find a missing set, okay? Because that will mean that the proposed listing is no good. Just like we had our missing number that we found. So we showed that this listing was no good, that there was no way to put the natural numbers in a one-to-one pairing with the real numbers, and we're showing that there's no way to put a set in a one-to-one correspondence with its power set either. Okay, so here's how we create the missing set. So it's a set, and it's made up of elements of S. Okay, so it should have been on that list, but we're going to make sure it's not. And we're going to make it different by one element from each set. So I'm going to be different from this set by one element. I'm going to be different from this set by one element, different from this set and this set by one element, and so on. I'm going to be different from each set. And here's the way we're going to be different. If A is in the subset that goes with it, then we don't include it. But A is not in the subset that's paired with it, so we are going to include it. So we're doing the opposite. B is in the subset that goes with it, and so we don't include B. So we do the opposite. So now the set M is different from the first set because it has A, and it's different from the second set because it does not have B. Now looking at C, the set with C does not have C, so we will include C. So we're always doing the opposite. So now set M won't be like this set that goes with C because it does have C in it. How about D? Should we include D or not? Yes, include D because it is not in the set that goes with it. So we're doing the opposite. D is not in this set, so we're including D. How about E? Should we include E? No. Good. Don't include E because this is S, the whole set, not the element S, but the whole set S. So E is in there. So don't include E. And then I'll put dot, dot, dot because there's some pattern going on in between. And then X, should we include X? Good. Yeah, include X because X is not in this set. So now we've created M, the missing set. It's not in this listing, even though this listing is infinite. It's not in this one-to-one listing because it's not a one-to-one listing. It got left out because it has, it differs from each of these sets that are listed by one element. So A was not in the first set, so we included A. B was in the second set, so we did not include B. So we always did the opposite. C, we included because it was not in this set that goes with C. And in this fashion, we're always different from every single set in this list. Well, that's a framing of the proof. We just create M. M is not in the listing of the power set of S. So there is no one-to-one pairing. And that means that the cardinality of the power set of S is always greater than the cardinality of S.
So who uses this in the real world?
That's a good question. I don't know. Mathematicians love this, but I don't know that set theories use that much in the real world. That's a very good question. I will look into that.
Okay.
Mathematicians probably enjoy chess too. You know, it makes your mind thinking. You think out strategies and why things work.
That's why I'm not a mathematician.
Okay. Well, you're not going to have to recall this proof, but I wanted you to be able to do your homework. So let's go ahead and look at your homework where you have this kind of a setup where you're finding the missing set. Now this isn't due for a while, but I just wanted to look at it with you since it's the type of problem we just looked at. So here's the set. The set is words. We have the words all, you, infinity, found, them, search, the, it. And then we have the power set of S. We have elements of the power set of S, not the whole power set. So we have subsets of those groups of words, and they're in one-to-one pairing with one of the elements. So for here, for example, all goes with the set all, infinity, found. You goes with the set it, search, them. Well, we're going to create the missing set, so you can write down M if you want, M equals, and then a set. And we're going to make a subset that's not in this list by using Cantor's diagonalization proof. So the word all is over here, and the word all is in the set with it, associated with it, so we do not include the word all in our set. Okay? The word you has the set it, search, them. The word you is not in this set, so we would include you. So we're always doing the opposite, so we include you. How about infinity? Should we include infinity?
No.
No. Good. How about found? Should we include found?
Yes.
So we have found and we have you. How about them? No. Don't include them. How about search?
No.
No. How about the? Nope. How about it? Yep. Okay. So you have the words you, found, it. Okay. And you'll have another problem like this as well, so you can work that out. There's a couple of other topics that I wanted to look at in this set, in this textbook, and so I think we'll look at it on the screen. So one of the things that I expect you should know is the answer to these first 4 questions. So at your desk, you can write down yes, no, or I don't know yet, because some of these we have not looked at yet. Okay. So the first question, is there an infinity that is greater than the infinity of the set of natural numbers, yet less than the larger infinity of the set of real numbers? Is the cardinality of the reals the next bigger infinity after the cardinality of the natural numbers? So that was the question we started the day with, and we haven't actually talked about it yet. So you can guess, and we'll look at the answer in a little bit. Number 2, is there an infinity greater than the infinity of the set of real numbers? What was our answer to that? We answered that. Yes, I see heads nodding. Good. We answered that last week. We found a set that had an infinity bigger than the set of real numbers. What was that set? Yeah, the power set of the real numbers. Good. Good. So that had an infinity greater than the infinity of the set of real numbers. Okay, how about 3? Are there infinitely many different sizes of infinity? Yes, good. I see heads nodding, because you can keep taking power sets of power sets of power sets, and there's no end to your ability to do that. Number 4, is there a largest infinity, one that encompasses all others? And the answer to that is no. I even see heads shaking no. Good. That's actually a paradox. When you try and make that set, it creates a paradox, and you can read about that in the end of your text here. Let's look more closely at our question of the day, finding an infinity between the infinity of the natural numbers and the set of real numbers. Let's see if I can find that on here. Why isn't the page down working? Okay. There we go. The continuum hypothesis. Here's our natural numbers. Here's our the real numbers is actually the same size as the power set of the natural numbers. So we have the continuum hypothesis. There is no cardinality between the cardinality of the set of natural numbers and the cardinality of the set of real numbers. That's a hypothesis, though. What is a hypothesis? Who knows what a hypothesis means? Yeah, it's a guess, an educated guess. So this has been a question since the late 1800s, and there's been a lot of work done on it. And the result is that the continuum hypothesis pushes us, in some sense, right to the edge of mathematical truth. Kurt Gödel in 1940 proved that it is impossible to disprove the continuum hypothesis. Then, in 1963, Paul Cohen proved that it is impossible to prove the continuum hypothesis. In other words, the continuum hypothesis can be neither proved nor disproved using the standard mathematical axioms and machinery. The continuum hypothesis is independent of our entire mathematical structure. The result, this is a result that's truly amazing, very unusual. Usually mathematicians work on a theorem or a hypothesis to get to be a theorem. When a hypothesis is proved, we call it a theorem. So mathematicians work away at it, numerous mathematicians around the world communicating and working together, building steps toward finding either proving something or disproving it. And here, it's been proven you can't prove it. It's been proven you can't disprove it. Very unusual, very unique. So the answer to the first question then is unprovable. Okay, so very first question here. Looks like the easiest question to answer, is there an infinity in between the size of the natural numbers and the real numbers? And the answer is that cannot be proven, it cannot be disproven. That brings us to the end of section 3.4, and we're going to move on into geometry in chapter 4. Does anybody have any questions before we do that? So some of you who haven't enjoyed the topic too much, the topics will keep changing fairly rapidly now, and there'll be more visual topics, more three-dimensional or hands-on. First we look in chapter 4 at section 4.1. A baseball diamond is really a square measuring 90 feet on a side. How far does a catcher have to throw the ball to get it from home plate to second base? So let's write down the work for this anyway. I won't write the title of 4.1 yet. See if you can, well, maybe you'll figure it out already. Maybe you figured it out already from what you brought to class here. Okay, so we have a baseball diamond, 90 feet on a side. It's actually a square. So put a couple of right corners there to show that this is a square. And the question is, how far does a catcher have to throw the ball to get it from home base to second base? So here I'll put D for distance. Anybody have any idea what we can do to figure out what this length is? Good, the Pythagorean theorem, and that is what this section is about. So who knows, what does the Pythagorean theorem say?
A squared plus b squared equals C.
Yes, indeed. Good. So if you don't have that memorized, do make sure you memorize that. And as you're using the Pythagorean theorem, it's used both ways. In a right triangle, that a squared plus b squared equals c squared. And if you have a triangle you don't know is a right triangle, you can check and see, does a squared plus b squared equal c squared? If it does, you've found a right triangle. Sometimes we use a double-headed arrow to show it goes both ways like that. Now as you use the Pythagorean theorem, make sure that the C is the hypotenuse. Put a star there. Your work isn't going to work out if C is not the hypotenuse. The hypotenuse is the side that does not make up the corner. It's opposite. It's opposite the right angle here. The two sides making up the right corner, this two sides here, these are the A and the B. And it doesn't matter if A and B get mixed up, but if you get C mixed in where A or B should be, then you're going to have a problem. So let's go ahead and answer this question. So the A and the B are both 90 here. And the C is the side that I labeled D. So you take out your calculator and you look at 90 squared. So we get 8,100, and then we'd add that up. 16,200. And then you would take the square root of both sides. Remember, when you're working with an equation, whatever you do to one side of the equation, do to the other. Now, as you're rounding these, round to the second decimal place. Well, I unfroze it. I complained about these document cameras when they brought them into Mac because they're not nearly as nice as the ones in the other buildings. They put all the controls on the front and they're all touch screens, so you're trying to write and you keep bumping them. So sorry. And sometimes they just turn off without me even bumping them.
Well, when you said round, do you want, like for example, do you want 127.3 or do you want 128?
127.28. So round to
you want two, okay.
two decimal
Yeah.
places if you're not instructed. And the rule for rounding is if the next decimal place after is 5 or above, then you round up. Yeah, and I guess these document cameras aren't even the ones that the school ordered. So I said, well, why didn't you make the contractor provide them? I guess they just didn't. Okay, anyway, so this is a 9, and that third decimal place being a 9 means that you're actually closer to 0.28 than you are to 0.27. So if the third decimal place is 5 or above, round up. And that would be feet. Does anybody have any questions on this problem? Well, there's two goals in this section that I have for you. One is to be able to use the Pythagorean theorem. So we want to make sure that you can find any missing sides of a right triangle. And the other goal is to be able to prove the Pythagorean theorem. So we'll start with the simpler and make sure you know how to use the Pythagorean theorem. So let's see if I have a few examples. Well, we should probably talk about why do we care? Why is the Pythagorean theorem important? Anybody have any suggestions why the Pythagorean theorem is important? In real life, why do we care about the Pythagorean theorem? Anybody have any ideas? Any of you ever help someone remodel a house? Or remodel your own house? My poor children grew up with their house being constantly remodeled. We just thought it'd take a couple years. We kept telling them, just help us out, and then it'll be done, and then you can have all your friends over and enjoy it. But it's just for kids, they moved out before it was done. Okay, so since we're always remodeling, my husband knows to take and tack the two pieces of wood together that he wants to make into a right angle. Take a ruler and mark off 3 feet and 4 feet, and then take not a ruler, use a tape measure, right? Mark off this 5 feet, and then once he's marked the 5 feet off, that's when he nails that solid, because then you have a right triangle. So you need to have the sides of your right triangle fit the Pythagorean theorem, or else you don't have a right triangle. So that's one of the things you can do to make your building nice and square. We all like having our walls stand up nice and square, not fall down. So some of the things that mathematicians enjoy are Pythagorean triples. Pythagorean triples are whole numbers that make the Pythagorean theorem true. So there's lots of ways to make the Pythagorean theorem true with decimals, right? Like 127.28 and 90 and 90. But whole numbers that make the Pythagorean theorem true are particularly interesting, and mathematicians search for larger and larger ones. We'll just write down a couple kind of small ones. How about 8, 15, and what's the other number? 17. So 8 squared plus 15 squared equals 17 squared. 8 squared is 64. 15 squared is 225. 17 squared is 289. And 64 plus 225 is 289. Here's another one. 5, 12, and 13. Which of these numbers would be the hypotenuse, by the way? 13, good. So the longest side would need to be the hypotenuse. So 5 squared plus 12 squared equals 13 squared. Five squared is 25. 12 squared is 144, and 13 squared is 169. 25 and 144 equals 169. In my last class, a student knew a third Pythagorean triple, or a fourth one. Does anybody know another Pythagorean triple? Well, you can investigate those on your own if you like. We're going to spend some time making sure you can use the Pythagorean theorem. So here's a right triangle. So the little corner that's drawn indicates that you have a right triangle. This is only true in right triangles. There's lots of triangles that are not right triangles, and then the Pythagorean theorem would not apply. So we have the 4 and the x and the 7. My husband sent me a joke. He texted to me. He said, "Dear algebra, quit asking us to find your x. We don't know why it left, and we don't know why." No, we don't care why it left, and we don't know why. Anyway, yeah, dumb math jokes. The other one he sent me was better. He said, "Come over to the nerd side. We have pie." All right, so which is the hypotenuse here?
7.
It's a 7, yes. So the sides that make up the right corner are the A and the B. Sides that make up the right corner are the A and the B. So the 4 and the x are A and B. And those you can get mixed up. It doesn't matter which is which. So 4 squared plus x squared equals, that's supposed to be a right corner there. 4 squared plus x squared equals 7 squared. 16 plus x squared is 49. Remember, whatever you do to one side of the equation, do to the other. So we'll go ahead and get the x by itself by subtracting 16 from both sides. X squared is 33. So x is, let's put that in the calculator. $5.74. So make sure you put the A and the B as the two sides that make up the right corner, the right angle there, and C is the other side. I'll try another one. Do you have any questions? So we have 3, 5, and x. Which one of those is C?
X.
Good. X is C, because the 3 and the 5 form the right angle. So 3 squared plus 5 squared equals x squared. 3 times 3 is 9. 5 times 5 is 25. So 9 plus 25 is 34. And then we'll take the square root of both sides there. .83. Wait a minute. I just had a 3, 4, 5 Pythagorean triple. Why didn't I get 4 for x? Shouldn't this be 4? 3, 4, 5?
Because the longest side's the hypotenuse.
Good, because the longest side is the hypotenuse, and so in a 3, 4, 5 right triangle, the hypotenuse is the 5. This one you can actually check if you printed out your template and you have a ruler with you, because the template was made for 3 by 5 cards. So this side is 3, this side's 5, and this side should be 5.83. So a little bit more than 5 3/4, and that is in fact what we see there. Here, we'll put one down for you to try, and just make sure that you have the hang of this. So go ahead and find x. And Nicholas and I can walk around and give you a hand if you're stuck. So if you're stuck, please raise your hand. So you should have made sure the 6 is the C, because the X and the 4 are making that right corner there, that 90-degree corner. Okay, so 4 squared plus X squared is 6 squared. That makes 16 plus X squared 36, or X squared 20 when you subtract 16 from both sides of the equation. So X is 4.47. Does anybody have any questions on that? Well, we're going to turn our attention to proving the Pythagorean theorem. I wanted to remind you that proofs have to be true for all different cases, and they have to be irrefutable. So I had some answers on quiz 1 that I wanted to just take a look at with you. So whatever root that you had to prove was irrational, I received answers that were incorrect because they said the square root, whatever the root was, goes on forever and doesn't repeat. The square root of 3 goes on forever and doesn't repeat, and then the people would write out the square root of 3 for however many decimal places their calculator went. And then they put a dot, dot, dot to show it goes on forever. The problem with this is that we only see 10 decimal places. How do you know it goes on forever without repeating? Your calculator didn't show you. It didn't go on forever. Your calculator doesn't go on forever. The reason we know it goes on forever and doesn't repeat is from the other proof that we did in class, where we proved that, well, if it was able to be written as a rational number, it would be A over B and so on. So this didn't give any points because it's the result of what we prove. It's not the proof. It's what we know because we proved the square root of 3 is irrational. So we're going to keep that kind of idea in mind as we look at the proofs for the Pythagorean theorem. But in the other class we did not have time for those proofs, and so we will stop here and pick up on Friday at this point. So if you didn't have your cutouts for today, you can bring them Friday. Also Friday, these are nicer if you have a ruler and graph paper. it will be a lot easier. So I'll see you on Friday. You can print graph paper online. You'll probably need about 10 pages for the whole semester. So, thank you.